Hey, hi everyone. So for this problem, an absorber plate with an area of incident, an area with the incident solar radiation at a rate of 800 watt per square meter. So 93% of the solar radiation is observed or absorbed by the absorber plate, while the remaining 7% is reflected away. The solar absorber plate has a surface temperature of 40 degrees Celsius with an emissivity of zero point 0.9 that experiences radiation exchange with the surrounding temperature of -5. In addition, convective heat transfer occurs between the absorber plate surface and the ambient air of 20 degrees Celsius with a convection heat transfer coefficient of 7 watts per square meter Kelvin. To determine the efficiency of the solar absorber, which is defined as the ratio of usable heat collected by the absorber to the incident solar radiation on the absorber. So, uh, let's imagine first the problem before we can solve it now. So, the problem says that we have a solar absorber plate. So, if you're not familiar with an absorber plate, it's like a solar PV module. Looks like this, and you have actually you have water, no? Or any solution that goes through this cross section of this pipe here. So this is a three-dimensional uh, absorber, no? But I will just show two-dimensional or the side view of this solar absorber plate. So we have given um, incident radiation or the irradiation. So we have Q here. We have Q that is incident radiation. So you have incident, no, radiation, which is 800 watts per square meter, no, this one. And then what happens, it is absorbed by the plate. So you have an absorptivity, no? So the absorptivity of the plate is also given. So meaning 93% is only absorbed by this plate, or 93% of the radiation, the 7% remaining is reflected away. So we don't care anymore about the 7%, no? And then the absorber plate has a temperature. So we have a temperature here. So on all the side, this is 40 degrees Celsius. No? So 40 degrees Celsius. Okay, and then you have an emissivity of zero point 0.9. So we have a given emissivity from the plate to the surroundings. And the surrounding temperature is -5 degrees Celsius. So you can imagine this is the far away temperature, no, from radiation. And then you have ambient air. So the ambient air is 20 degrees Celsius with this given convectivity transfer coefficient. So we have a lot of things given here, no? And how do we solve for the efficiency of the solar absorber? So to find the efficiency of the solar absorber, this is just the ratio of the usable heat, no? So the Q usable versus the available or the irradiation, no? Or the incident, no? So how much is utilized basically? How much radiation is utilized by the absorber? So how do we find the Q usable and the Q incident? So for the Q incident, we can solve this. Since we have an area, we can just multiply no, the heat flux and the area. But for the Q usable, this is much more a little bit complicated, more complicated than that. Since we have convection, no, and radiation, no, as well. So you can imagine the absorber plate is absorbing this radiation, no. So you have this one, and then some of it will be expelled, no, or irradiated into the surroundings, which is -5 degrees Celsius. And then some of that will also be convected away, no? So you can imagine if we do a heat balance, no? If we do a heat balance, so everything that this will experience, so let's say imagine we have what goes into this, no, to this node. So you have the Q incident, Okay, okay, and then that's it. No? So that is the only one going through the surface, no? So everything goes in, and then everything goes out is equal to everything that goes out. So you have the Q convective, you have also the Q radiation, no? No? And then actually also the one absorbed, no? Q absorbed or usable. I'll just write here the absorbed, no? Absorbed. Okay. So this will be the absorbed. So we have most of the variables given here, or the parameters needed to solve this. So we can solve for the Q absorbed. So you can say that the Q absorbed, so the heat absorbed by the solar absorber will be Q incident minus Q convective heat, and then minus the radiative heat. Okay, so don't get things wrong, no? This is also radiation, no? But this is the radiation dispersed from the atmosphere. And take note of the direction that I used here. It is going to the surrounding. Since we have a temperature of 40 degrees, the surrounding is -5. So they're going from a high temperature to low temperature. Same goes with convection. So solve this. Uh, okay. So Q incident is just equal to the heat flux times the area, no? So this will be just 800 watts, or actually it's better to just write the formula first, no? And then minus Q convective. So the Q convective is HA. This is convective, no? And then A, and then the temperature of the surface and the temperature of the air, no? So I'll just write here air for now, and then minus the actually we forgot the ano dito, no, the absorptivity, no? So there should be an absorptivity as well here. Sorry, we should include the absorptivity. So for the Q-rad, we have the emissivity, so it will emit outwards. So we have epsilon, we have sigma, and we have the temperature difference of the surface in fourth power and the surrounding. No? Or I'll just write here, sir. No. So that's it. So we have this given, this is given, this is given, this is given. Actually, we forgot the area here. Sorry. So given, this given, given. Okay, everything is given, so we can solve for this. So the absorptivity is 93, no? So 0.93. And you have Q 800. So I will not write the units for now, but you can analyze this and this will still be correct. So 5, and then H conv, so 7. You have the area, so 5. Ts minus the air, so we have the temperature of the surface is 40 minus this will be 20. Okay, minus the area again, so 5. Epsilon is what? Do we have an epsilon? Sorry, yeah, we have 0.9, the emissivity, and then Ts, T surface. So this should be an absolute temperature, no? So we have 40 plus 273 to the fourth power minus -5 plus 273 to the fourth power. And so to find the Q absorb, we have solve this. We have to find the calculator. Okay, so this will be 0.93 times 800 times 5 minus 7 times 5 times 20 minus 5 times 0.9 times you have 40, so 40 plus 273 to the fourth power, and then you have uh minus -5 plus 273 to the fourth, and then that's it. So oh, Did I miss something? 7 times 5 times. So this will be just 20. 5 times 0.9. I forgot the constant. Stefan Boltzmann constant. We forgot the Stefan Boltzmann constant here. Anyways, you can just write this down. So 5.67 times 10 to the negative 8. So the Q absorbed will be 1800 88. No? So 1887 watts. No? So that's it. So we have the Q absorbed, but we forgot, no? So this should be the efficiency. To find the efficiency, you just divide this 1887 watts. Sorry, that's too much. Watts divided by the incident. So the incident radiation is actually not really this, no, since this is with absorptivity. So we have the bare incident radiation. So this should be um 800 only, no? So you have to take note of this. You can imagine you have in your steam power plant, you have the heating value as your basis for efficiency, right? So it's like this at this scenario. So you have 5 square meter. So this will be 800, sorry, not 887 over 800 times 5. Okay. So this will be 0.47, 4717. So 47.18% loss. So in percentage na lang. Okay, so that's it.